Welcome to this video. In this video, I will be talking about Hamming code and Steane code, and I will also talk about linear codes and dual of a code. The idea will be to introduce parity check and some other matrices that concern to the syndrome detection and correction in case of classical error correction codes, and later we will see that these matrices can also be generalized in the quantum case. So in the Hamming code, I will talk about very briefly what is the main takeaway or what is the main idea behind the Hamming codes. I will not go through each and every detail of the Hamming code. So let's start. Our working example will be for Hamming codes will be I have total 7 physical bits or encoded bits, and there will be 4 logical qubits. So I will encode a 4-bit message into a 7-bit total message. So here I have shown it. So let's see. So here I am showing the 7 bits. So A, B, C, D and Z1, Z2, Z3. The idea is A, B, C, D is my original message, and Z1, Z2, Z3, these are something called as parity check bits. So so ABCD, let me repeat, ABCD is my original message, and Z1, Z2, Z3 is what we call parity check bits. So why we call this parity check bit is because it relates to ABCD in a particular way that I am showing here. So as you can see that Z1 is A plus B plus D, Z2 is A plus C plus D, and Z3 is B plus C plus D. And everything in this is modulus 2. So this is addition modulo 2 or the XOR operation. So from this you can see that if one of the bits get flipped, for example if my A bit gets flipped, then the Z1 parity will change. So because the number of zeros and ones will change, and essentially Z1 is calculating the number of ones which will flip its sign. So that's the main idea, and you can nicely capture this using a Venn diagram. So the idea is you have A plus D plus B, and that is Z1, and similarly you have Z2 which is A, D and C, and similarly you have Z3 which is B, D and C. Now what happens, you can check that the syndrome measurement will help us detect where the error has occurred. So suppose what I do is I get a syndrome measurement where Z1 and Z2 have flipped their parities. Then I know that the error must have been either, not either, it can only be one thing, that is A. Because if the error is D, then Z1, Z2, Z3, all of them will flip their parity. So that's the main idea. So for example, if my error is B, then Z1 and Z3 will flip or show the parity change. If my error is C, then Z2, Z3 will show the parity change. And in this way I can detect exactly which of my 4 bits the error has occurred. So now let's go to the linear codes. So this is the like before this the Hamming codes which I discussed, it was very briefly, and now we go to linear codes. So linear codes are such that the code space forms a subspace of Z and 2, and here Z is simply 0 and 1, and the size of the space is 2 power k, and this is what I write as n comma k. So this particular nomenclature here says that I have encoded k bits into n. So this nomenclature is what I used in the Hamming codes also, where I had encoded I had encoded 4 bits into 7 bits. So n was 7 and k was 4. So it was a 7-4 code, the Hamming code. And now we come to the idea of what is a generator matrix. So a generator matrix is nothing but it is a matrix such that the range space of that matrix, is simply the code space. So that's the main idea. And in general, the generator matrix is a matrix of n cross k dimension. So let me write it here. So generator matrix is n cross k, where as I said, I am encoding k bits into n bits, and everything is classical here. And now, what is a parity check matrix? A parity check matrix is a matrix such that the code space is the kernel of that matrix. So it's kind of opposite of the generator matrix. So I have defined it here. So it consists of all the codes such that they are annihilated by the parity check matrix. So here it should have been H. So let's correct it. H Y equal to 0. So this should be the generator, this should be the parity check matrix, and this is the generator matrix I have defined here. So to get an idea, we can look into the generator matrix and parity check matrix of the Hamming code, the 7-4 Hamming code that we saw just now. So for this, the generator matrix will simply be a 4x4 identity matrix and a matrix A which is 3x4, and A is defined in this particular fashion. So why is this so? Because it is easy to see that when I have the multiplication of generator matrix with A, B, C, D, I will generate Z1, Z2, Z3 such that Z1 is of this form. So Z1 is A plus D plus B. So that is simple to check. You can do the multiplication. So this is the idea behind the generator matrix. And in general, a generator matrix is of this form. And similarly, a matrix H is a parity check matrix, and it is always of the form that I am showing here. So it has some A which is unique to the code. So here it is 3 cross 4. And the identity matrix is 3 cross 3 for the 7-4 code. And in general, a generator matrix is of this form. A generator matrix is of this form. So it has identity on the space of k cross k bits. And it has then the A matrix. And similarly, the H matrix is of this form. And now we can show that indeed H is such a matrix that the kernel of H is actually the code space. So to see this, you can just take the generator matrix and multiply it with the code. So Gx, so this generates the code space. So X is the original message. So this is the original message. And I multiply it with the generator matrix, I get something like this. And then I multiply it with the parity check matrix, that is H. And multiplication will give something that is 2AX. Now the fact that 2 appears and everything, the entire arithmetic is done modulo 2 means that this is 0. And that's the main idea, that the code space is the kernel of the parity check matrix. Now if you have a code word Y and then you have an error E, then the parity check matrix is such that it annihilates the code word and keeps the error. So the information about the errors and the syndromes is contained in the parity check matrix, and so it is a very useful way to understand error correction. So for example, I have written the syndrome for the 7-4 Hamming code. So here the idea is that I have a message and I have some error on the message, and this means now after the error the new message will be acted upon by the parity check matrix. And once I do this, so the parity check matrix is n minus k cross n, and I will have a n cross 1 matrix acting on it, and then I will generate a n minus k syndrome, that is S1, S2, S3. So here the idea is that if my syndrome is 0, 0, 0, what this means is that I should have A plus B plus D as Z1, A plus C plus D as Z2, and B plus C plus D as Z3. So in other words, my original message is same as my final message, and there is no, like the parity check bits did not flip in the sign, or did not flip from 0 and 1. So there was no bit flip in the parity checks. So this means that syndrome 0 corresponds to identity. Now what happens if I have a S3 parity syndrome, S3 syndrome and a S2 syndrome? So my syndrome is of the form of 0, 1, 1, for example. If my syndrome is of the form of 0 1 1, it means the error has been such that there has been a flip on the second bit and the third bit. These parity checks were violated. So this means if I go back to my Venn diagram, so the third bit and second bit parity check violation means a C error. So I will associate 0 1 1 with a C error. So this is the main idea how you can do syndrome correction. Similarly, if suppose my parity or my syndrome, sorry, if my syndrome is such that it is 1 0 1, then I know my parity checks at the first Z1 and Z3 is violated, and then I can look into the Venn diagram to say that the error was a B error. So this is a B error. Similarly, now I have the idea of this errors in the case of Steane code. But before going to the Steane code, I will just mention what is a dual code for a code C. So a dual code is kind of a dual space or to a vector space, or it's kind of a dual set basically. So C perpendicular is the symbol that we associate with the dual code. It consists of all those y belonging to z and 2, so strings of n bits, such that y dot x is 0, and this dot product is bitwise dot product. So it's XOR operation xi yi, and for all x belonging to C. So this is kind of an example of if you have a cone, we have seen that there is a dual cone. Given a cone, there is a dual cone K star. So this is kind of a similar definition. So with this we go to the Steane code. So in the Steane code, the stabilizer S, the set of stabilizer is given in this particular fashion. It has 6 elements. So I have 6 elements, and it is a 7. It is a 7 1 3 error correction code. This means it has 1 logical qubit, 7 physical qubits, and it can correct both phase flip and bit flip errors, and hence it can correct any error in a qubit. So what is the main idea behind the Steane code? I will discuss that. So the idea is to borrow the intuition from the Hamming code. So I had 7, so not double brackets. So I had 7 for the Hamming code, and there I can rename my Z1, A, B, D, C, everything. I can rename them to get some sort of an equation that looks like this. So these are the syndrome equation, and you can see that there are 3 syndrome equation which corresponds to the flip error, and the intuition is that you will have 3 stabilizers that correspond to the Z stabilizers, so which take care of the bit flip, and similarly to correct the phase flip you will have 3 more stabilizers that are of same form, and they correspond to the correction of phase flip error. So this is the main idea that's why I have shown this 3 equation of syndrome. But now let's forget about this. So let's forget about this for a moment, and now focus on the stabilizers. So what is the idea? The idea is that stabilizers will commute or anti-commute with the error, and this anti-commutation of the stabilizer will generate a syndrome. And now we have to show that we are producing unique syndrome for each of the bits. So I have 7 bits, so I should have in principle I have 7 bits, and there are x, y, z errors, and these all should be unique. So let's look into that. So for this it is important to arrange these bits in a particular fashion. So this is what I have shown here in this triangular graph that I have drawn. So here this part 1 2 3 4, it corresponds to Z1, Z2, Z3, Z4. This part corresponds to Z2, Z3, Z5, Z6, and similarly this part corresponds to Z3, Z4, Z6, Z7, and I have a Z placket of this form, and similarly I have a placket for X. So I have in total two different triangles, which is for X and for Z. And now the idea is, suppose I get a error at the first bit. So this is a error. So let me use a different mark. So if this is the error, then this placket will be anti-commuting with the error, and this will glow up. For example, this will register a -1, and this can be captured by the syndrome extraction that we have seen in the previous videos that I have shown here. So if you have X1, you have 6 different syndrome outputs, because there are 6 stabilizers, and one of the stabilizer anti-commutes and it registers a 1. Now suppose I have a X2 error, that is this error on this part, then you can see that it overlaps on both left hand side and right hand side. So it will register a glow or a -1. It will anti-commute with these two stabilizers. So this I have shown here with 2 1s. Similarly, you can see that X3 anti-commutes with all the 3 of them, and hence this I have shown by this 3 1s. Now if you have X4, then it registers a different relation, X5 registers something different, and X6, X7 registers something different. Similarly, if you have Z, in the case of Z, it will anti-commute with the triangle of X. So instead of these plackets, you can think of them as now representing X3. Instead of Z3, you can write X3, X4, X6, X7. So in this way, you can have these error correction by measuring this, and this is called a type of color code. It is a subset of color codes, and I will not go into detail of that, but in the next video I will talk about CSS codes. So let's go to the next video.